any questions? So we'll talk a little bit about digital circuit principles and logic circuits, the different classes, the difference between positive and negative logic, what a frequency divider looks like, and truth tables. So in modern amateur radio, typically have quite a few digital circuits. So not that long ago, they were mostly all we were like software defined radio, less and less analog components, digital domain, digital signal processing, where you can filters, amplifiers, all kinds of things with mathematics. The digital logic, except for the ones we talked about in tri-state, it has two states, true or false, high or low, 1 or 0, and we call positive logic when we use the high voltage to represent a 1 and low voltage to represent a 0. In the older, like TTL and older CMOS, we would run everything at 5 volts. So the logic 1 would be 5 volts, and logic 0 would be 0 volts, although there's some range on it. In case of negative logic, it's just the opposite. Negative logic used that often, but it depends on the application. And it's a test question. What does positive logic mean in reference to logic devices? Okay, we have gates. So on the bottom left, we have the careful AND gate, a 2-input AND gate. When both of the inputs true, the output will be true. So A and B gives you C. Any other combination is going to be false. On the left, have a AND on the bottom. If I had A and B true, instead of it being the output being true, it's going to be false. The output is going to be true for everything else. If they're both 0 or one of them is 0, it's going to be true. So it's just the not or inverse of the other one. It actually turns out most things are built out of NAND gates because when you actually build it out of transistors, it's easier to make a NAND than it is a NAND. It takes an extra transistor. And it works better with the Morgan theorem and some of those. Okay, so a truth table is just how you represent those states. So you just do it in a little chart and you show all the possible input states. So A can be 0, 0, 1, 5. B can be 0, 1, 0, 1. There's only 4, since there's 2 inputs, there's only 4 possible configurations for states. And then the Q output is what the output is for each one of those states. So represent NAND. And when you write it, line over the top indicates that it's not. So AB means A and B, not A. So what logical operation does a NAND gate perform? Well, it's fully. Now we have a two-input OR gate, and that's the truth table. And the way you represent it is for an OR, it's A or B with a plus. So, and I don't know why B and Q are white and A is not, but anyway. In the case of the OR gates, if either or all inputs are true, the output is true. It's only false when none of the inputs are false. I mean, all of them. Yeah. What logical operation does an OR gate? Okay, now we make it a NOR gate. So it's an OR gate. So what changes on the truth table? It's the inverse. So it's only a 1 when all the inputs are 0. And this is actually, this truth table is showing both of them, the OR gate and the NOR gate. A lot of times on particularly flip-flops, you will see a Q and a not Q. You'll have both states represented. Typically flip-flops. Yeah. It's coming. So we have to do an exclusive NOR first. And an exclusive NOR is a circuit that really tells you when the input is different. So you see from the truth table, this one, because it's a NOR, it's saying it's true when they're both same, either both 0 or both 1, and 0 when they're different. If it was an exclusive OR, it would be only 1 when both of them were different. 0, 1, 1, 0. Well, you need that. You have to find differences. You have to say you discriminate things. They're the same or they're different. And that's what that is telling you. It's the same or difference detector. So you've got two signals, and you know whether it's 1 or 0, whether they're both the same or they're both different. What logical operation is performed by an exclusive NOR gate? NOR, yeah. Exclusive. Exclusive NOR gate. Yes. If you take a bunch of NOR gates, AND gates, and you hook them together, you can have a circuit that remembers the state as long as it has power. So I can set it up so the output of Q is a 1, and it will do that as long as until I input a signal that changes the state of it to 0. But the case, just to show you what we call a D flip-flop, such as there's JK flip-flops, RS flip-flops. Typically, you use a D flip-flop for something like a storage register where you want to sample a bunch of bits and hold whatever state that is, so that then you can look at the output and do something with it. So you normally have these several in a package, so you can build what we call a register. Whereas the JK flip-flop is a lot more complicated. This D flip-flop is pretty simple. When you have a clock signal that rises, whatever the state of the D input is what the Q output goes to. So it just samples the input. Until you get it. Put back to the input. Every time you get a clock signal, it's going to see what is the opposite of what it was. So it's going to toggle. Well, that a toggle to the clock is going to change from 1 to 0. So it's actually a one-bit counter. If you put a bunch of them together, outputting what I think I said. Yeah. And when you get the clock, okay, the output is going to be whatever is on D at the time the clock goes through. And it's on they clock on the edge of the signal. So if I mentioned if I connect it up with this output back to the input, I get a toggle, or I can connect two of them together like this. So whenever the not Q output changes, it clocks the second one, which is also looking at what is not Q output. So each one of those is going to toggle every time there's a clock signal. So I get the first clock signal, and this is going to change state. If that results in not Q going true or high, that's going to clock this way, and it's going to toggle to a different state. So the more of these connect together, and it's called ripple counter, because there's one clock and then it sort of ripples through it. And the outputs are what you see down here in your diagram. So each one of these clocks going through, or in this case, because it's got this little symbol here, it's an inverted clock. So this one's going forward. A lot of devices will trigger on a positive going, a lot of them on a negative going, and they use either a little circle or one of these kind of symbols to represent that it's a negative going clock. So every time that clock changes state, then you're going to see it count up. So we did 4 clocks, and we wind up with, we start at 0, 1, 2, 3, 4 states. Here's 0. That's 0. 2, 3. I tried to do this in my simulator pointedly. Their representation of these flip-flops don't have a reset. So I couldn't. Right. But this configuration, we're counting up to 10 and then generating a reset pulse to start over. So it would be a decade counter. And so, good way to get rid of it. So, which one? That one? Yeah. Nope. So you can see it as it counts up and this output stage, okay, based on the number of clocks. So when it gets up to 9, it should generate a reset pulse instead of back to 0. But because the flip-flops in my simulator don't have a reset pin, I can't do it. So I can count it 0 through 9 and got to pretend that it's reset. Otherwise, you can find the frequency of a pulse. Like, that's not divide a signal frequency by 16. That's wrong. So it's power to. And there you go. 1, 2, 4, 8, 16. Well, if I have 4 bits, okay, I have one of them represents a 1, 0, 1. The next one represents 2. The next one represents 4. The next one represents 8. Okay? So if they were all true, in other words, 1, 1, 1, 1, that would be 15, right? We'll start with 0. So 0 to 15 is 16. Does that make sense? Okay. If we had a fifth one, to get a 17th count, I'd have 1, 0, 0, 0, 0. Well, it takes, if you start with 0, so if I have 16, that's 17 stages. So you've got to count for 0 as one of the possibilities. He gets confused. But you don't have to know hexadecimal or octal. Octal 3 bits. 0, 3, 7, 8, 8. It's important to remember because when we talk about digital modulation, when we talk about FT8, it does 8 represents 3 bits. That's a symbol with 8 different components. So what was the answer? What's the function of a cascade counter? There was a little device invented, has to be at least 50 years ago, an NE555. They still make them. It's been used, and it can be a monostable multivibrator, a bistable multivibrator, or a half-stable multivibrator, all in the same little 810. You get a package. I think it might have a surface mount. So if it's a monostable, it means it's only stable in one state. So another name for it is called one shot. So you give it a trigger pulse, or like a clock, and it will output a true or a positive pulse for a period of time. There's an RC, time constant network associated with it that determines how long that pulse is. So it's very useful for a lot of things where you need to generate a pulse of a certain length. And it's kind of an analog type, this digital analog type device. In its bicycle mode, it acts like a flip flop. So it toggles like a D flip flop with this output connected back to its input. So every time it's clocked, it changes state. It's on bi-stable, two stable states. Then there's the active mode, there's a free running oscillator. So it just sits there by itself and just toggles back and forth. And the width of that and the frequency is determined by that RC network. Actually, there's two resistors, so it's not exactly 50-50. Here's how you would hook one up as a monostate. And you get an input trigger pulse, and it's going to generate this output like this, depending on how long it takes to charge up that capacitor. And it charges through this resistor R1. And there's a threshold detector here when it gets up to a specific voltage. That's when it changes the output. So it's kind of like we learned on the regular time constant, which was the resistance times the capacitance. So this has got a little 1.1 factor in it because of the way it's built. When we do it as a bicable, we're going to slightly different. There's no need for a capacitor because it's just changing its toggling from one state to the other, and it maintains that state until you trigger it. So essentially, another way to make the flip flop. In the astable mode, we're back to the charging a capacitor. This one now through two resistors. So both of the resistors are required to charge it up. Only one of them is required to discharge it. So it's on time versus off time. It's slightly different because of the change in value. But it'll just give you a constant square wave. They only work in basically audio, lower, maybe up to a megahertz. So which circuit is bistable? Which of the following is a circuit that continuously alternates between two states without an external clock? What's the characteristic of a monostable vibrator? Unstable state. So state